Make sure we are up and running on the lesson page. And we're looking good. Okay, so today we are working on understanding scatter plots. We also had a question about area of surface area of shapes, since yesterday we talked about volume, and I'm going to answer that at the end of the video today, as along with the other questions that come up. So today let's get through understanding scatter plots, and we'll get that surface area question answered shortly. Okay, I want to go ahead and just get the comments set up. Go ahead and start posting any questions you have, and we'll get started momentarily. Just 1 minute. We'll wait for a few other people to jump on. Okay, so we are finishing up with the geometry section of our review, and we are getting into the statistics sections. This will be our last week of the free summer review sessions, and we're opening up the seats to reserve your spot in this fall's algebra and geometry daily help sessions. All right, so understanding scatter plots. So a scatter plot is a graph that shows a relationship between two variables in a data set. Each point on the scatter plot represents an ordered pair of data, and this table and graph show the same bivariate data, and bivariate data involves two variables. The pattern shown from plotted points provides a representation of how the data are related. So what we looked at is, let's say there was a survey that was done, or they looked at several cars in a parking lot. They took the age of the car and they ran a value of what it could potentially sell for in thousands of dollars. And they just went down this list. And this happens all the time when we're trying to test a hypothesis in science or many applications, is to collect data and see if there is some type of decision that can be made from the data that we put together. So is there a pattern? Is there some kind of connection between how old a car is and how much it's valued, how much you could sell it for? So we're going to talk about some of the keywords associated with identifying that connection. So down here we can see when comparing the table and the scatter plot, notice that the scatter plot shows that older cars have less value than newer cars in most cases. This relationship is much more obvious in the scatter plot than it is in the table. Okay, so it's not always the case because they just went down a list of cars in the parking lot, and it's only looking at the data of how old the car is, what year it is, and how much it could be sold for. Maybe they looked up the blue book as they're walking down the parking lot. So now some of these, it's not always the case, right? So some of these cars are very old but also have a high value. So in this case, here's one that's a little bit of an outlier. We'll talk about that in a minute. And in this case, it's still valued high, right? The y-axis talks about the value, so the higher it is, the higher it's valued. So this is 6 years old, and it looks like it's one of the most valuable cars on the lot. Well, maybe that was a sports car or a higher end brand that was costed more to buy to begin with. Okay, so we're looking at we're looking for a trend. All right. So again, when comparing the table and the scatter plot, notice that the scatter plot shows that older cars have less value than newer cars in most cases. This relationship is much more obvious on the scatter plot than it is in the table. So that's why we created the scatter plot, so that we could have a easier to understand representation of the data that's easier for the human eye and brain to understand. So let's look here, and we have an outlier is a value that is much greater or lesser than most of the other values in the data set. And you can easily identify an outlier on its graph. So they're talking about that same point that we found, right? So that 0.6 and $9,200 is an outlier, showing that one of the 6-year-old cars has a value considerably greater than most of the other cars that are about the same age. So data can cluster around a line or around a point. So a cluster is a set of closely grouped data. The data points on the graph appear to cluster around a line. And because of this, you can say that the data set has a linear association. If the points do not cluster around a line, then they have a nonlinear association. Okay, so linear association can be positive or negative, and because the line on this graph has a negative slope, the data have a negative association. So as the age increases, the value decreases. If both data sets increase together, then the data would have a positive association. So if we look over here, if we were to draw a line, it doesn't have to be perfect, but if we were to try to make a line that was as good of a representation as we could of this data, it might look something like this. Okay, so that orange line that we drew kind of goes right in the middle. It's kind of the average. It's right in the middle of that cluster. And that's the line that this data is clustering around. As we can see, this has a negative slope, where if we were walking from left to right, we would be going downhill, right? So this has a linear association, but is also a negative association. And the association between two data sets can also be described as strong or weak. The association shown in the scatter plot, and in the scatter plot we just looked at, is strong since the data are all very closely clustered around the shape of the line. So if we look at this, for the most part, aside from the outliers, they're all following this pretty narrow corridor, right? They're all fitting right pretty closely, for the most part, right around that orange line. So that would be a strong association. Let's see this next example and tell me if this would be a stronger or weaker association than the one we just looked at. And I think you would agree that this has a weaker association, because if we were to try to create a avenue for all of these points to fit in, it's a wider street, so to speak, right? So there's more variation. It still looks like there is some type of linear association from what we can tell. And it is positive, because if we did have to draw a line right between those, right, maybe where that shadow is falling might be a good spot. And between the two pencils and pen here is where they're all fitting. So the closer together all of the points fall within this corridor, that would be a stronger association. The wider apart would be a weaker association that was talked about in this last sentence here. Okay, so in this example, it's asking us to use describe if any data, and we really just did that. So it does follow a positive sloped line, right? But it is certainly, so it's a positive linear association, but it's a little bit weaker than the one we looked at a few minutes ago. Okay, and indeed, positive linear association. So describe the association of data, if any, in this scatter plot. So they are grouped pretty closely together, but could we draw a line through here? And remember, when you draw this best fit line, you want to see as many points above, right? So we can kind of draw a line through there, but we have to ask ourselves, when we're standing at this point in the line, we would want to see as many points below the line over here as we see above. So in this case, we don't see any down here. So we did not draw a very good best fit line. It works pretty good for the middle, but then again, something at the top happens where we have these 3 points above the line, and we would expect to have 3 points over here to balance it out. So really what we see here is, if we had to draw a line, it might look something like maybe something like that. So there is certainly a strong association, because they are all really closely following this line that I was able to draw, which we could assign an equation to that. We're not going to do that today. So there is a negative correlation, because the overall slope is negative, right? If we're walking from left to right, we would be going downhill. So there's a correlation or association. It is negative, and it's non-linear is how we would classify and describe this association. Okay. I'll leave that up for just a moment. Checking any questions we have. And we'll get back to that in just a moment. So look over this example 2. Let me know if there's any questions that come up for that. Okay, moving on. So this next data set shows the grades of for individual students in 2 of their classes, and each pair of scores are earned by 1 student. Okay, so this is 1 student's data. So this particular person received a 93 in history and an 82 in English. This next person received an 82 in history and 80 in English. This next one, 93 in history, 95 in English. Okay, so each column is a person. And it's asking us if we're to construct a scatter plot here. Let's see if we can make one of these. To draw some axes for us. So let's call Y the English grade. And X-axis the history grade. Then we need to assign a scale. So let's make, what's the lowest number we have here? We have a 68. Do we have any numbers lower than 68? No. How about down here, what's the lowest number we have? Looks like 66. So we can actually start this graph. We can do one of these where that is 0, 0, but we have a break in the scale. So let's call this 65, 70, 75, 80, 85, 90, 95, 100. Didn't do a great job of leaving space on that one. Do the same over here. Start at 65, 70, 75, 80, 85, 90, 95, 100. Okay, now we're looking at the data up here. Let's see if I can maybe even fold this over so we can get it all to fit on the camera for us. Okay, so history is here. So the first one, we're going to go to 93, which will be somewhere between here and here, and we're going to go up to 82 for the English grade. Then over 80 and up to 82. Over to 95 and over to 93 and then up to 95. Over to 75 and up to 78. Over to 68 and up to 75. 87, 95, 85, 86, 73, 68, right about there. Next we have 85 and 66, 75 and 98, 78 and 90, 70 and 95. Now, so far, is there any type of correlation? We have a positive slope or a negative slope, or does it seem like things are all over the place? Start thinking about that. Okay, so that should be all of them. If it ends up being where you can't seem to find a pattern of what's happening here, then we would say that there's actually not an association at all, or if it would be extremely weak if there was. But for our purposes here, unless it's obvious that there's some type of grouping or corridor, or here, it all remains really all over the place. So what this is saying is that there's really not a association between someone's history grade and English grade. So you could have someone that gets a very high score in history and a low score in English, like this person, or vice versa. They could get a high score in English, but pretty low in history, right? So, or both. They could do poorly at both or great at both. But this is an example of there being, that's the plot we made, just like so. And there's really not a strong association. So let's interpret this example. So it's asking us to interpret this scatter plot. So if we look at each of these points as a student of they're taking math and they're taking science, and the higher we go up here, that's their science grade, and the higher we go to the right, that's this particular person's math grade. So let's look at this outlier just to practice on this one. So they got a 90 in math, but if we go over to where that would intersect the y-axis, if we drew this line over here. So they got about a 68 in science, but they did very good. They got a 90 in math. So this is certainly in the outlier, but that was a practice on getting a measure of each of these points. So this person over here, they got a 97 about in math and about 92 in science. This person down here looks like they did poorly in both of those classes. They got a 68 in math and a 75 in science. So what do you think? Is there an association? Is it linear? And is it a strong or a weak association? What do you think? So if we tried to draw a corridor, they definitely seem to fit for the most part within this corridor here, in this little hallway we made. And they're pretty tight together, right? So if that shadow from the pen was the best fit line, and they all fit in that pretty narrow hallway, so that would be a strong correlation. It does follow a linear relationship, right? So that would be a linear association. And if we were walking from left to right, that would be an uphill journey. So that's a positive slope. Okay. So again, the math and science scatter plot shows the data with a positive linear association, and the plot shows that students who score high in math also score high in science, except for that one outlier. And it also implies that those that score poorly in math score poorly in science. All right. So here's another one. Now, some of these, when there starts to become a weaker association, actually, we've got our new terminology down here. So a straight line that shows the linear relationship between points of a scatter plot is called a line of best fit. A line of best fit may pass through all the data points, some of the points, or none of the points. That in all those three are okay. So it may pass through all the data points. It might pass through some of the points, or it might pass through none of the points. It's really kind of an average of, if you were to kind of squish the points or take an average of how far away the points are from the line. That's how a computer, for example, would calculate the line of best fit. It's calculating what minimizes the average distance between the points and a line that you draw. When drawing a line of best fit, try drawing the line as close as possible to all of the points with an equal number of data points above and an equal number of data points below the line, while ignoring the outliers. You can also use a graphing calculator or a computer spreadsheet program to construct the lines of best fit. So the line of best fit can help you determine the strength of an association. If the data are closely grouped around the line of best fit, the association is considered to be strong. If the data are loosely scattered around a line of best fit, the association would be considered weak. Okay. All right. So looking at this example, you can use these two papers. So example 5, let's see if there is a linear relationship or non-linear relationship or no relationship, or association rather. Is it a strong or weak association? Is it a positive or negative association if there is one? Now, if we were to start to, it looks like they are having a negative slope in general. If I started to squeeze these two together to narrow this hallway, so we already knocked out one. I would call that one an outlier, so let's ignore the outlier again. We want to cover up as few points as possible to identify what this hallway is going to look like. Okay, so it looks like that's a medium-sized hallway, so it would not say it's a strong association. And if I now drew a line right in the middle of this hallway where all of the points fit, I might have something straight line like so. And if I did it right, I should have about as many line dots above the line as below. So we had about 1, 2, 3, 4, 5, 6, 7, 8, 9, 10 above. And as far as on or below, we have 1, 2, 3, 4, 5, 6, 7, 8. So maybe not a perfect line of best fit, but it's okay. And after we do that, so we made the hallway, knocking out 1 or 2 extreme outliers, and we had a medium hallway. So that may not be a super strong association, but it's just an association nevertheless. It is a negative linear association because it did generally follow a straight line. And let's start to interpret this now. So if it's video games and grades, we can say there is a negative association between your grade point average and the number of hours spent playing video games according to this study. Okay, now it's not 100% true because this particular person plays 16 hours of video games per week and has not nearly 100% on their grade point average. But that's an outlier, right? So maybe they're particularly talented in this class or whatever the case may be. But generally, okay, so these people over here that spend very few hours playing video games have the A's in the class. And over here, generally, according to this study, the people that are spending 15, 20 hours per week playing video games are getting like C's or worse, right? So that's how we can interpret that. So that is linear association. It's negative, and it's not the strongest. There's a decent one. So that was their line that they drew. And suppose I shouldn't have put the arrows on. We're going to talk about that in a minute with interpolation and extrapolating. But this is the line that they drew. So mine was pretty close. So again, it's not a strong association. It's a weak negative linear association. Okay, so for the students who spend more time on games, generally receive lower grades. Okay, so when a scatter plot shows a strong association, you can use the line of best fit to make predictions. If your prediction is between points you are given, you can interpolate. If your prediction is outside the range of the data given, you extrapolate. Usually, interpolating data is more accurate than extrapolating data. Usually, the further out from the data you estimate, the less accurate your prediction is likely to be, right? And that makes sense because if we were to say, okay, well, let's say if someone plays 100 hours of video games per week, that doesn't even make sense, right? So if we followed this line and we went out to 100, would they have a negative GPA or grade point average? Well, it's not even possible, so it just doesn't make sense. They probably would have close to a 0 GPA, but it wouldn't be negative, right? If we were to extend this, it would end up going past this x-axis. If we went all the way over here, then that line of best fit would be negative. So that's what it's talking about. The further out you go, it tends to be less accurate. But so that would be extrapolating. If you're trying to figure out if someone did outside of the study, So in this particular case, the person that played the most video games was here at 19 hours. If you were to say, well, I wonder about what the GPA would be of someone that played for 22 hours, let's just say. So this would be extrapolating. We went over here to 21, 22. So now we're extrapolating. And what we would do is we'd continue this line here, make it a bit longer. So if we were extrapolating and someone asked, okay, based on this data, so I played 22 hours, so what do you think my GPA would be if I played 22 hours of video games? So we go extend the line of best fit, go directly up from the 22 on the x-axis here. Then we go directly left and see what that number that we're touching on the y-axis. So for students that play 22 hours of video games, half of them are going to fall below this line and receive less than, say, 70% is the expected score based on the pattern. So that's line of best fit and extrapolating and interpolating. All right. So let's do a couple more examples. Feel free to post your questions if you have questions about the material covered tonight, or maybe you're finishing up a summer school class and got stuck. I can help you with one of those questions as well. Just take a picture and put it in the comments, of course. And we do have a couple more of these to practice. Okay, so use the following scatter plots to answer questions 1 through 4. So which scatter plot shows no association? Remember, when we're looking for an association, we're trying to build a hallway, so to speak, or this little corridor. So graph A, like certainly if all of the points fit inside of this very narrow hallway, well, that's going to be a strong positive association. How about B? There's not really a way that you can make a hallway that is clear that shows some type of logical pattern happening. When we do C, all of the points fit between these two pens, so they fit in this hallway, but look at that shadow that's being made by the pencil here. That would be if we tried to force a linear best fit line, it wouldn't really go through half of the points, right? So if we looked at this, at that particular spot, there's 2 points above the line of best fit if we drew it on the shadow, and none below it over here. Same thing here. There's a whole bunch in this section below the line of best fit and none above the line of best fit north of that shadow. So, but it is a tight grouping. It's just a curved hallway, right? So that would be a non-linear association. Now graph D, there's certainly a clear hallway that could be drawn like this. It would be a negative association, but notice the hallway is not very narrow. It's not, if they all fit in this narrow hallway, that'd be a strong association. So that's a weak negative linear association for D. So going back here, so which scatter plot shows no association? And that would be graph B, right? So graph B shows no association. Question 2. I'll leave this up for 1 minute to let you try to attempt to figure out number 2 on your own. That's the one we're working on. Try that on your own, and we'll do that together in just a moment. Okay, question 2. So which scatter plot is most likely to display the relationship between the time it takes to drive from a house to a certain school, Y, and the distance between the house and the school? So let's read this again for understanding. Which scatter plot is most likely to display the relationship between the time it takes to drive from a house to a certain school, Y, and the distance between the house and the school, X? Okay, so it would make sense that if you have a bigger distance from school, it's going to take longer. If you lived across the street from the school, a short distance, then there would be almost no time to get to school, right? So how about graph A? How about that? So if your distance was almost 0, if you lived across the street from school, you just have to walk across the street and you'd be at school. So that the Y is the time it takes, right? What if you're 50 miles away from school? Okay, x-axis was the distance. Then we would go up, walk over to the y-axis, and that would be a very large amount of time that it would take, and all of these points in between. And there's a very strong association because typically everyone maybe averages their trip at a rate of 25 or 30 miles an hour if you factor in all of the lights. So there's a very strong correlation between 1, 2, 3, 4, 5, 6 miles and how long it's going to take to get to school. So that's going to be A. Looks like a good contender to answer question 2. So I'll give you a moment to think about question 3. Give you a minute to think about that, and we will do that together in just a moment. All right. So question 3. Which of the following correctly relates a term and the scatter plot? So let's look at each of these one at a time. Would you think weak association and graph A are connected in any way? I would say no. Remember the association. If it's a strong association, the hallway that they all fit in is very narrow. A weak association, like question A is asking, would be maybe still a positive. You could tell that there's a positive slope going on, but you need a wide hallway for them all to fit in. How about B? So linear association and graph B. No, I don't think so. There's really not any association, right? The data is really all over the place. So I'd say linear association and graph B. I don't think so. How about nonlinear association? and graph C. So there is an association. They're all very, they follow this curved line very nicely, but it doesn't fit in a line, right? If anything, we would have to draw a curved line. So this does not have a linear association. So a nonlinear association for graph C, that's a good one. That's a good option. And graph D, strong association. No, A had a strong association because they all fit in all the data points fit in a very narrow hallway. Graph D, not so much. You need a wide hallway to get all those points to fit in the same hallway. So the only one that makes sense here is C, a nonlinear association, graph C. I would agree with that. Okay, problem 4. I'll leave you to that one for a minute to think on that one. Okay, let's work on 4 together. How many of the scatter plots shown have a negative association? So not negative association in like weak or negative isn't bad, but a negative association, remember, is like a downhill slope if we were to walk the slope from left to right. A, positive association. So that doesn't count. It's not going to factor into how many have a negative association. B would be no association. I can't really find a slope that makes sense. Graph C, there is an association. It's nonlinear, but it is negative. It's downhill all the time during this association. If we were to draw a line right in the middle of all those points, it would be negative, have a negative slope, just nonlinear. So that one counts. That is a negative association. And graph D, it's a weak association. They're not tightly grouped. But if we had to draw a line, a linear sketch would make sense. It would go right through the middle of all of those points. And it is downhill if we were to walk this hill from left to right. So how many have a negative association? That would be C and D, 1 and 2. So answer choice C is what we're looking for number 4, answer choice C. All right. I'm going to do another example. I'm done with the statistics for today. Go ahead and post any questions that you have if you're watching the rerun of this, and I can answer it during the next live session. So I'm going to set this aside. We did have a question that came in from yesterday. We were going over volume yesterday. They had a question about surface area. Just asked if we could do an example of surface area. Okay. So yesterday we did an example with volume, and volume would be like if we were filling this with water. So this is a cylinder. This particular example, we dropped a marble into this graduated cylinder or beaker, not sure which one it is. And it caused the water level to rise by this much. So if we were able to find the volume of this little cylinder here, that would be the same amount of water displaced or liquid in whatever type of liquid was in there. And that was able to help us find what the actual volume of the sphere or marble that we dropped in here as well. So volume of a cylinder is talking about how much is inside, like how much we could fill it with. As an example of a surface area, call it S area, surface area. This is a formula for if you were to paint, how much paper, like wallpaper, if you were to wrap this in, that would be surface area. So notice the two formulas and how they're different. So the volume takes the area of the base, right, the area of the circle, and extends that a certain distance h. Okay, so it takes the area of a circle and stretches the circle in a third dimension. When we're talking about surface area, we're always talking about a two-dimensional measurement. Okay, so area is going to be a units squared. A volume is going to be a units cubed, right? So we're a minute ago, this gave us centimeters cubed. When we find this, we're going to be doing, maybe we'll put 2 centimeters, 3 centimeters, and the answer is going to be in centimeters squared. Okay, so let's break this down. Now 2 pi r is the formula for the circumference of a circle. So we're kind of like the perimeter of a circle. So 2 pi r would be how much fence you would need to put around a circle, right? So it's how many centimeters if you're to walk around this, how many centimeters it would have taken to do so. Now we multiply that by h, which would be the distance from top to bottom. And this is going to give us, if we were to unwrap this label and think of this like a soup can or something, if we were to take the label off of this soup can, we would actually end up with a rectangle. Yeah. Maybe something like this. And it's going to be like rectangular in shape. So if we unwrap this, like if these two ends were together and we unwrapped this label from this can, that would be the area, and we would actually end up with a rectangle if we were to fully flatten this label out. It would end up being a rectangle. And this dimension here would be your h, and this dimension here would be your 2 pi r number. Now, we recognize pi r squared. Pi r squared is the area of a circle. So pi r squared would be like the area of this circle. Okay, so pi r squared would be like the area of one circle. And that's why they have the 2, because so this is the area of the bottom of the can. And then the area of the top of the can. So we have the bottom and the top, right? So that's why that's what the 2 is there for, because it's 2 times the area of a circle. Okay, so we kind of get that. Let me know in the comments if you need some clarification on that. And let's go through a quick example of if we have an area when the radius is 2 centimeters and the height is 3 centimeters. So let's do a quick calculation to practice this. So we do 2 pi blank blank plus 2 pi blank squared. And if I'm going to plug in the 2 is the radius, I'm going to plug the 2 in, that 2 in here, and also over here. And maybe I'll do the height in blue. And we're plugging that in for this h here. So what would this turn into? So we have 2 times 2 is 4, times 3 is 12, times pi, don't forget the pi, Now here, order of operations, we're going to want to square this first. So that's going to be 4, right? 2 squared is 4. 2 times 4 is 8 pi. Now we can add those two together, right? We have 12 pi and 8 pi. Those are going to go together and become how many pi's? 12 plus 8 is 20. So if we wanted to leave it in terms of pi, we could do that. If it wanted us to round to the nearest decimal, we would multiply this by 3.14. Let's just do that for fun. So we could do 20 times 3.14, and we'd have 62.8. Either one. Okay. So thank you very much, everyone, for participating, and thank you for submitting your questions on Florida Math Live. You can post those throughout the evening and tomorrow morning as well, and I will be back to answer your questions tomorrow, same time, same place. I'll stay on for just one more minute if there are any more questions. Okay?